Toward the end of World War II, the emergence of combat jets in Germany and Japan served as a massive wake-up call. This pushed the U.S. Navy to immediately launch a massive program to re-equip its carrier air wings with the latest technology. In 1944, three leading aircraft manufacturers, McDonnell, Vought, and North American, received a critical assignment. They were tasked with developing initial designs for jet fighters. These aircraft needed to guarantee reliable air defense for an aircraft carrier within a 3 nautical mile radius. On top of this tough challenge, the aircraft designers were flooded with urgent orders from the Navy brass. The military was rushing to upgrade its aircraft ahead of the full-scale invasion of Japan, planned for 1945. Each company was pushing the envelope to build the best aircraft possible. They incorporated the most advanced and radical technical solutions into their designs. The most innovative of the three proposals turned out to be the Vought FI 340 design. In late December 1944, the military signed a contract for several test aircraft. This agreement also included a first batch of production fighters, designated the F6U. Following the company naming tradition, this brand new fighter was officially named the Pirate. During the F6U development, the biggest challenge for the engineering team was reducing aerodynamic drag to an absolute minimum. To make the fuselage as thin and streamlined as possible, designers opted for the compact Westinghouse Model 24C turbojet. By the time Vought engineers were getting ready to assemble the first prototype, Westinghouse had already started production on the engine. This specific engine received the military designation J34WE22. It was designed with a 250-hour operating life between overhauls and weighed in at roughly 1,168 pounds. The exhaust nozzle was routed beneath a short tail boom, which housed the conventional empennage. The engineers neatly tucked the small NACA inlets right at the wing roots. The wing itself featured a straight design. It utilized a custom airfoil with a 12% thickness to chord ratio. But the most striking feature of the Pirate was its completely new, incredibly strong, and surprisingly lightweight construction material. Patented by Vought, this unique development was a composite sandwich. It consisted of a layer of ultra-light balsa wood bonded between two thin sheets of aluminum. These layers were pressed together and baked inside a massive autoclave. This innovative composite was called Metalite. Its incredible strength and rigidity allowed designers to significantly cut down on the internal structural frames. These frames typically support the aircraft's skin. Thanks to this change, the airframe became much lighter and virtually monolithic. Panels made from this material covered almost the entire surface of the aircraft. To minimize drag, they were fastened using special flush rivets. The parts were manufactured so precisely that the gaps between the skin panels were practically invisible. As a result, after final painting and careful polishing, the fighter's perfectly clean lines impressed even seasoned aviation experts. It looked as if the entire aircraft had been cast from a single piece of metal. Compared to its competitor, the North American XFJ1, the F6U Advanced Composite Skin saved roughly 2,200 pounds in overall weight. This was an absolutely monumental achievement for the era. The short and slightly rounded nose section of the F6U fighter gave the pilot an excellent field of view both forward and downward. This detail was absolutely critical since landing a jet on the narrow deck of an aircraft carrier is no easy task. On top of that, it was on this exact model that Vought used a modern tricycle landing gear setup. They included a nose wheel for the first time in their history. This made ground handling significantly easier. During the aircraft's development, engineers put a massive focus on pilot comfort. They wanted to minimize the physical effort required to fly the airplane. To pull this off, they hid special aerodynamic balances inside the wing, making sure there were no protruding parts to disrupt the airflow. The elevator was also fitted with extra stabilization systems. All these clever design choices led to an incredible result. The maximum stick force the pilot had to apply during maneuvers dropped to just 10 pounds. This made flying a whole lot more pleasant and way less exhausting. Wind tunnel tests fully backed up the designer's initial calculations. However, during these tests, the engineers did not look into how the aircraft would handle at speeds approaching Mach 1. They didn't account for the complex aerodynamic effects of compressibility. To avoid complicating things and to save precious time, the developers took the easiest way out. They simply added automatic, hydraulically actuated dive brakes to the airplane. This system artificially capped the top flight speed. It safely kept the fighter out of those dangerous, unexplored areas of the flight envelope. The Pirate boasted some seriously powerful built-in armament. It packed 4 20mm cannons, each with an ammo capacity of 150 rounds. These guns were mounted directly under the cockpit. The muzzles were positioned right in the nose of the fuselage. But there was one glaring issue. The engine air intakes were located right down there too. Because of this, the risk of the engine ingesting gun gas during heavy firing was incredibly high. These fears were immediately confirmed during the first live fire tests. Even so, nobody took the time to fix such a major flaw right away. Company management just wanted to get the new fighter up in the air as quickly as possible. They figured they could refine the design and iron out the bugs later when prepping the airplane for mass production. What worried the engineers a lot more was how low the engine exhaust nozzle sat relative to the aircraft's thrust line. Designers were afraid that changing thrust might cause the fighter to pitch up or down uncontrollably. To thoroughly check how the aircraft would handle in real-world conditions, specialists built a scale model of the F6U. They simulated the powerful blast of hot exhaust gases by hooking up 6 compressors that blasted high-pressure air through a special hose connected to the model. These tests were carried out in the low-speed wind tunnel at the United Aircraft Research Division in Hartford. The results of the experiments were a pleasant surprise. Across 4 different simulated flight conditions, the nozzle setup did not cause any dangerous pitching moments, so they decided to leave this unusual engine layout exactly as it was. The first prototype of the XF6U fighter was assembled in the summer of 1946 at the plant in Stratford, Connecticut. After completing its initial ground tests, the aircraft was disassembled. It was crated up and trucked clear across the country to Muroc Army Airfield in California, where it was reassembled. On October 2, 1946, veteran test pilot Boone Guyton took the brand new fighter up for its maiden flight. However, the debut almost ended in disaster. Mid-flight, the single engine on the XF6U Pirate suddenly failed. Fortunately, Guyton managed to stick the aircraft to a safe emergency landing. He brought it down on the massive dry lake bed of Rosamond Lake. Back then, its perfectly flat surface was heavily used at Muroc as a natural runway. The culprit behind the sudden engine failure turned out to be an experimental oil spray lubrication system designed by Westinghouse. The problem was that the 6 gallons of oil loaded into the aircraft before the flight had simply evaporated and burned off in less than an hour. That was exactly how long it took the ground crew to complete the engine warm-up, taxi tests, and the takeoff itself. Once the oil ran dry, the turbojet engine predictably ceased from severe overheating. With no spare engine anywhere on base, the flight test program had to be suspended immediately. The aircraft wouldn't fly again for another 45 days, but the team's bad luck continued. Shortly after their 3rd flight at Muroc, a torrential rainstorm moved in. Keep in mind, this base was located deep in the Mojave Desert. It was roughly 100 miles northeast of Los Angeles, so you can imagine how incredibly rare a downpour like this was for such a bone-dry region. The rock-hard surface of the dry lake bed instantly turned into an impassable mud pit. Because of this freak weather, all further flights were scrubbed indefinitely. To make the most of this forced downtime, the test crew focused on analyzing the flight data they had already collected. Back in 1946, this telemetry was captured using what we'd now consider a pretty primitive setup. It was essentially an enclosed photorecorder fitted with duplicate flight instruments, a lighting system, and a standard gun camera. This setup would continuously record every twitch of the instrument dials onto film, frame by frame. The gauges inside the box mirrored exactly what the pilot saw in the cockpit. These included airspeed, rate of climb, precise altitude, outside air temperature, and fuel flow. The box also recorded a bunch of other critical parameters for the turbojet. This gave the engineers a reliable record of exactly what the aircraft was doing in flight. Unfortunately, this gathered data told them almost nothing about the aircraft's actual flight dynamics. Critical metrics like roll and pitch rates, control surface deflection, and G-load simply weren't being recorded. The engineers had to burn a ton of precious time just trying to calculate the true Mach number. Back then, they had to rely on standard slide rules for the math. This made the whole data reduction process incredibly slow and tedious. A few weeks later, the dry lake bed was finally firm enough for takeoffs, and testing resumed. During the 10th flight, the airplane was pushed to its limits, around Mach 0.8. Suddenly, the pilot felt sharp, violent kicks through the rudder pedals. Subsequent flights at speeds between Mach 0.76 and Mach 0.8 didn't provide any clear answers. The team couldn't find a consistent pattern linking the kicks to airspeed. They urgently called in a panel of leading aerodynamicists. They reached a unanimous conclusion. The culprit was localized shock waves. These were forming right at the intersection of the vertical stabilizer and the horizontal tailplane. It was a high-speed compressibility effect the designers simply hadn't accounted for. Vought found itself in a tough spot. They had neither the time nor the budget for a complete tail redesign. So the engineers went with the quickest and simplest fix. They installed a bullet-shaped anti-shock fairing right at the intersection of the horizontal and vertical stabilizers. This fix was immediately applied to the second prototype, which was still being assembled at the Stratford plant. Meanwhile, the end of World War II triggered massive cuts in military spending. This directly impacted the Navy's orders for the F6U Pirate. The Navy seriously scaled back its requirements, slashing the production order to just 30 aircraft. In the spring of 1947, Vought finally completed the second XF6U-1 prototype. The aircraft was flown under its own power to Muroc Army Airfield. The cross-country journey required 4 fuel and maintenance stops. At each stop, Vought ground crews were waiting to quickly turn the fighter around for the next leg of the trip. However, during subsequent flight tests, another major flaw emerged. The fighter suffered from poor directional stability. The aircraft continuously yawed from side to side. The oscillations took entirely too long to damp out. Pilots openly complained about unpredictable handling and sluggish rudder response. To fix this, engineers significantly increased the vertical tail area on the third prototype. This larger tail not only restored handling, it also improved the aerodynamics at the stabilizer intersection at high speeds. As a result, the designers were able to ditch the forward section of the anti-shock fairing they had installed earlier. In the fall of 1947, the first 2 prototypes were ferried to the Naval Air Test Center. They were sent there for evaluation by Navy aviators. Paul Thayer was assigned as the lead test pilot for the Navy. Interestingly, this project tied him so closely to the manufacturer that Thayer later became the president of Vought. After the company merged with a larger corporation, he eventually served as chief operating officer and vice chairman of the board. The feedback from the Navy pilots on the performance of the F6U Pirate was brutal, to put it mildly. And honestly, it was completely justified. The airplane was a mediocre performer. The main issue was the power plant. The J-34WE-22 engine was severely underpowered. It also suffered from incredibly sluggish throttle response. To make matters worse, right around this time, the Navy introduced much stricter standards for jet engines. Power plants were now required to sustain maximum thrust for 2.5 times longer. On top of that, the Navy demanded the engine spool up from idle to full power 6 times faster than previously required. With such demanding new standards, the shortcomings of the engine threatened to put the final nail in the coffin for the entire fighter program. The saving grace was the arrival of the first turbojet to meet the new military specifications. This was the Westinghouse J-34WE-30, along with its upgraded afterburning version designated as the J-34WE-30A. This afterburning variant produced almost 4,190 pounds of thrust. That was roughly 1,190 pounds more than the previous underpowered engine could deliver. Naturally, the designers decided to drop this new engine into their aircraft right away. As a result, in 1948, all the experimental XF6U-1 prototypes had to be shipped back to the Stratford factory for a complete power plant swap. Because the new engine was longer, engineers had to extensively redesign the airframe. Due to the high exhaust temperatures, the tail section of the jet was skinned with special aluminum sheeting. To track exactly how the metal was heating up during flight, they applied a unique temperature-sensitive paint. This paint changed color as it got hotter. The aircraft had also put on weight, shifting its center of gravity. To compensate, designers had to increase the wing area by adding large triangular extensions to the trailing edge that spanned almost a quarter of the entire wing. The developers were also mindful of the earlier directional stability issues of the fighter, so they added small, oval-shaped vertical fins to the horizontal stabilizer. The aircraft finally had an afterburner, but its use came with strict limitations, making the new feature somewhat impractical. Flight manuals restricted afterburner use to just 2 to 3 minutes during takeoff and climbed to 29,500 feet. Similarly, pilots could only light the burner for a mere 2 or 3 minutes at a time during intense dogfights. The reason was simple. Engaging the afterburner caused fuel consumption to instantly spike by a massive 30%. Despite these restrictions, the F6U Pirate made history as the world's first production fighter equipped with an afterburner. It provided a significant performance boost. Hitting the afterburner instantly added 50 knots to the airspeed. With these upgrades complete, the experimental X prefix was dropped, and the military began evaluating the pre-production F6U fighters. Final flight testing for the upgraded F6U Pirate took place at the Naval Air Test Center. During one of the scheduled flights, test pilot Paul Thayer was handed an ambitious objective. The objective was to hit maximum speed with the afterburner lit at an altitude of 12,000 feet. Taking to the skies, the pilot headed east. Once he was roughly 30 miles out from home base, he lit the burner. Almost instantly, as Thayer himself later recalled, a massive explosion rocked the tail section where the engine was housed. The jet immediately lost hydraulics, and a large portion of the cockpit instruments went dead. Fortunately, the airplane still responded to the flight controls. Thayer kept his cool. After quickly declaring an in-flight emergency over the radio, he began a gentle glide back toward the airfield. Flying right alongside him was his chase plane, a piston-engine F-8F Bearcat. The chase pilot got on the radio and reported that from the outside, the F-6U showed no visible signs of catastrophic damage or even a fire. When Thayer reported that he had lost his airspeed indicator, the chase pilot pulled off a masterful maneuver. He tucked in tight next to the damaged F-6U Pirate, flying essentially wingtip to wingtip. He started calling out airspeeds over the radio using his own instruments. Without that vital data, safely landing the crippled jet would have been flat-out impossible. Since the hydraulics were out, he had to bring it in for a gear-up belly landing. The touchdown went surprisingly well, and Paul Thayer walked away from the crash without a scratch. The fighter itself, however, was damaged so severely that it was written off as a total loss. But the fact that the pilot managed to get the aircraft down in one piece allowed engineers to thoroughly inspect the wreckage. This helped them pinpoint exactly what caused this near-fatal accident. It turned out that the turbine shaft's front bearing had shattered in mid-air. Its metal fragments got sucked right into the compressor, tearing through absolutely everything in their path and shredding the engine's entire core. Sheared compressor blades punched right through the aircraft's skin, slicing through critical hydraulic lines and severing the pitot static lines. It was sheer luck that this shrapnel missed the flight control cables. In this crash, the fighter's rugged fuselage design proved its worth, essentially saving the pilot's life. Ultimately, in 1949, all testing for the F-6U Pirate was successfully wrapped up, and the jet fighter was officially accepted by the Navy. However, deliveries of the production aircraft to the military were delayed. The reason for this was Vaught's major relocation to a new manufacturing facility near Dallas, Texas. Previously, the massive plant had belonged to North American Aviation. The company had been gradually winding down mass production of its legendary P-51 Mustang fighters there, following the end of World War II. To get set up at their new location, Vought had to move over 15 million pounds of cargo. They accomplished all of this using a fleet of flatbed trucks over a distance of nearly 1,400 miles. Along with the tooling and equipment, around 1,300 company employees relocated to Texas with their families. This monumental move was finally completed in April 1949. Along with the factory equipment, the first 3 production F-6U fighters were trucked over to the new site. They were fully assembled and thoroughly inspected at the new Dallas facility. But then another unexpected problem came up. The new plant's runway was just too short for jet aircraft. So while construction crews rushed to lengthen it, the initial test flights for the new jets had to take place at the nearby airbase in Ardmore. That is exactly where, on June 29, 1949, the very first flight of a true production standard F-6U took place. Production of these fighters proceeded at a pretty sluggish pace, with about one brand new F6U-1 rolling off the factory floor every week. In total, to fulfill the government contract, only 30 of these aircraft were built. The final production fighter came off the assembly line in February 1950. Interestingly enough, one of these standard fighters was later converted into a dedicated reconnaissance aircraft. It received the new designation F6U-1P. That same year, in 1950, a bizarre and terrifying incident happened to Navy test pilot Chen Chandler, who routinely flight tested the production aircraft. Observers up in the airfield's control tower were keeping a close eye on a standard F6U takeoff. Suddenly, instead of rotating smoothly off the runway, the aircraft violently pitched up and shot into the sky almost vertically. For several long seconds, Chandler didn't respond to their frantic radio calls. Finally, his heavy sigh of relief came over the frequency. After that, he leveled the fighter out and brought it back around for a safe landing. When a sweat-soaked Chandler climbed out of the cockpit, he explained exactly what had gone wrong. During his takeoff roll, he pushed the throttle forward and kicked in the afterburner. But the thick leather glove on his left hand unexpectedly got jammed right between the throttle and the elevator trim wheel. As he tried to yank his pinched thumb free, the pilot accidentally jerked his hand and rolled the trim wheel. That tiny bit of movement was more than enough to aggressively pitch the aircraft's nose up. This sent the heavy jet rocketing into the sky. Fortunately, despite the massive G-loads and the initial shock, Chandler managed to keep his composure. He regained control of the situation and put the airplane safely back on the runway. Overall, the career of the F6U Pirate in the Navy was pretty much a bust. Compared to newer carrier-based fighters like the F2H and F9F that hit the fleet in 1949, along with the 1950-era F7U, this aircraft was practically obsolete before it even entered service. As a result, the Navy used it strictly for training or various research and development projects. The total flight time logged by all 30 production aircraft combined was a mere 945 hours. In fact, some of these jets logged less than 6 hours of total flight time over their entire lifespan. That means those specific aircraft only flew twice. They flew once for their mandatory factory test flight and once for the ferry flight to their assigned base. The only place these fighters saw any real use was with Air Development Squadron 3, VX-3, operating out of Naval Air Station Patuxent River. Structurally, the F6U-1 Pirate was a conventional low-wing monoplane with a single vertical tail. To improve in-flight stability, the wings featured a slight dihedral. Additionally, 2 auxiliary vertical fins were added to the horizontal stabilizer. The oval-shaped fuselage consisted of 3 main sections. Up front, the cockpit was fitted with an ejection seat from the renowned British manufacturer Martin Baker. A clear teardrop canopy covered the cockpit, sliding aft for access. Beneath the cockpit floor, the aircraft packed a heavy punch, housing 4 cannons and their ammunition boxes. To make servicing the guns and reloading quick and easy, large rectangular access panels were located on both sides of the fuselage. The short, rounded nose section was divided into upper and lower compartments by a structural bulkhead. The upper compartment housed the radio gear and a gun camera to record hits. Meanwhile, the lower bay held the cannon barrels and the nose landing gear mechanism. The cannon ports were cleanly covered by aerodynamic fairings. Directly behind the pilot was a self-sealing fuel tank, with its filler neck extending to the top of the fuselage. It held about 320 gallons of fuel. The core of the design was the center fuselage, built around a highly reinforced structural frame. This served as the primary attachment point for the main wing spars, the engine, and the arresting hook. The forward and center sections were skinned with panels made of a specialized composite material called Metalite. After painting, the entire surface was polished to a mirror finish to reduce aerodynamic drag. In the tail section, which was covered in lightweight duralumin panels, they placed a dual-mode afterburner enclosed in a heavy steel casing. To keep the metal from melting under the extreme heat, cooling air constantly circulated between the afterburner and the casing. This air was drawn in through dedicated scoops on the belly of the aircraft. Thanks to this clever cooling setup, the temperature of the outer aluminum skin never exceeded 1100 degrees Fahrenheit. Running along the upper part of the fuselage, right above the engine and afterburner, was a heavy structural spine. The vertical stabilizer was mounted directly to this beam. To protect the pilot and vital systems, the center and tail sections were securely separated by a dedicated firewall. The straight, tapered wing was equipped with conventional ailerons and flaps. Right at the wing root, the designers added large fillets, which significantly improved the aerodynamics. The wingtips were designed to carry auxiliary drop tanks. Each of these held 140 gallons of fuel. Bright landing lights were built directly into their noses. Interestingly, the wingtips themselves were specially shaped to generate an airflow. This airflow would safely push the empty tanks clear of the aircraft when jettisoned. The tail section featured a massive vertical stabilizer, along with the horizontal stabilizer and elevators. To make the aircraft easier to handle and reduce pilot fatigue, the elevators were fitted with trim tabs. The pilot could control these using a trim wheel located on the left side of the cockpit. Right at the very top of the vertical stabilizer sat a pitot tube. The aircraft used a tricycle landing gear configuration, complete with a steerable nose wheel. Now here's a really interesting and important feature. Once on the carrier deck, the nose gear strut could be compressed, allowing the aircraft to kneel. This caused the tail of the aircraft to tilt up significantly. Thanks to this clever trick, the pilot could safely taxi around the deck using the jet engine. This aimed the hot exhaust blast safely over the heads of the deck crew. Production F6U fighters were powered by the Westinghouse J-34 jet engine. Its standard thrust was around 3,000 pounds. And when the Afterburner was engaged, that figure jumped to almost 4,200 pounds. It is worth noting that official manuals usually quote ideal test stand numbers. But on an actual aircraft, installed thrust is always a bit lower. For the F6U, this installation loss was a full 12%. The J-34 engine itself was pretty advanced for its time. It featured an 11-stage axial flow compressor, an annular combustion chamber, and a 2-stage turbine. The air intakes for it were neatly tucked underneath, right at the wing roots. The airplane was also equipped with hydraulically operated speed brakes. They served an incredibly important safety function, deploying entirely automatically the moment the fighter hit a critical speed of Mach 0.8. The armament of the F6U fighter was quite powerful, consisting of 4 20mm M3 cannons. It carried 150 rounds per gun. The avionics suite included a standard radio, a radio compass, and a revolutionary piece of tech for the time. This was an APX-1 IFF, or Identify Friend or Foe system, which the United States military used on this aircraft for the very first time.